Good evening, everyone. So today is our revision session for our course Computational Fluid Dynamics by uh, Professor Srinivas Jayanti, Department of Chemical Engineering, IIT Madras, and I am your TA Manjunath, Research Scholar from the Department of Applied Mechanics and Biomedical Engineering, IIT Madras. So in the last few weeks, we have seen we have last learned weeks we have learned through different aspects of CFD and how a fluid flow can be modeled for CFD, starting from the basics and covering all the aspects like discretization, uh, basic concept, solution, and how different mathematical mod- modeling and aspects can be incorporated in the CFD. So uh, this week we'll actually in this session we will actually go through some of the key or important aspects of the course to uh, revise what is important for the exam perspective or exam point of view. We will be revisiting some of the important questions and concepts which will be useful for you when you will be attending the exams, and also to understand to the basics or the core fundamentals of our course CFD, computational fluid dynamics. So in the last 11 weeks, we have covered pretty much. So this section will be uh, covering or revision for all these sessions for you to easily revise for your exams and all. Session. So I'll be giving some questions to you. Uh, I'll read out the questions for you and take some time to understand the question and try to recollect what we have studied, what you have studied from the videos as well as our interaction sections, and try to answer the question. Then I will explain I will give you the answer and explain the question. But you please do try to answer the questions. It will be very useful for you uh, once for the exams of this course. Okay, let's start the session. First question. First question is on discretization. Which of the following formulae is a good approximations of dou square u by dou y square at grid point I comma j? So the question is asking uh, the approximation for dou square u by dou y square at a grid point I comma j. So which among the following best is the best discretization or approximation for this particular partial differential equation, partial differential term? Okay, so option 1, first option is u j minus 1 comma I minus 2 times u j I plus u j plus 1 I the whole divided by delta y square. Option B, u I j minus 1 minus 2 times u I j plus u I j plus 1 by delta x square. Option C, u I comma j minus 2 times u I j plus 1 plus u I j plus 2 the whole divided by delta y square. Option D, none of the above. So it's a second order term here, dou square u by dou y square. So try to recollect how we have discretized this equation in the past, and how which method or which scheme we will be choosing for discretizing second order spatial derivatives. This is a second order spatial time. So how such kind of terms are we are which is the scheme we will be using mostly to discretize such methods? Try to recollect and answer the question. Excuse me. So our answer is option D, none of the above. So why is it? So let's see how we will be discretizing this thing. So let us consider a discretized uniformly discretized structured grid. This one with delta x is as the increment in x direction and delta y as the increment in y direction. Let's take this is our point P I comma j. So the question is asking how to discretize uh, uh, dou square u by dou y square at this point. Dou square u y square at this point. So uh, if you recollect the Taylor series approximation, from the Taylor series approximation, okay, let us discuss what is how we will be using Taylor series to approximate partial differential times. So first, let us see how Taylor series can be used for this. Let's see if there is a function f of x which can be written as its value can be expressed using Taylor series expansion uh, with this equation called Taylor series expansion. That is f of x is its value at point I can be uh, uh, approximated with f of xi plus x minus xi dou f by dou x at I plus x minus xi the whole square by 2 factorial into dou square f by dou x square at I plus etc. Up to, if it is an nth term, for the equation for the nth term will be x minus xi the all raised to n by n factorial into dou raised to n times f by dou x raised to n plus higher order terms, where this will include all the terms that is n that is greater than n. Terms greater than n will be represented by h. So if there is one small increment in this uh, I plus 1 term, that is uh, next adjacent term for this particular f of x is f of I plus 1, which can be represented by f of x I plus 1. So we are only replacing the x in this particular equation. In the above equation, x will be replaced by x plus 1. That's a simple difference we will be having. So the equation becomes f of xi plus xi plus 1 minus xi into dou f by dou x. So here we have replaced. Again, the x here will be replaced by xi plus 1. This xi plus 1 minus xi the whole square by 2 factorial into dou square f by dou x square plus h. So we only need up to second order. So for this particular problem, that's why it is being truncated here. So if we are looking on the backward side or the uh, reverse direction, where it is one uh, term less than the f of xi, then that will be f of xi plus xi minus 1. Here x will be replaced by x of I minus 1 in all the times in this equation. Then that will be f of xi minus 1 minus xi into dou f by dou x at I plus xi minus 1 minus xi the whole square by 2 factorial, then dou square f by dou x square plus higher order terms. From this we can get uh, first equation. From the first equation we can take f of this particular term, say partial differential term dou f by dou x at I. It can be termed as f of I plus 1 minus f of I by xi plus 1 minus xi minus the higher order terms. Similar to that, from okay, this can be here it is having this particular term also. If I am only taking what first order term dou f by dou xi, then this can be approximated to this particular equation. Dou f by dou x at I is equal to f of I plus 1 by f of I by delta x. This particular term is the delta x, that's the increment in x at I plus all order of terms in delta x. So the other terms in the order of delta xi we are truncating here. Similarly, if we are taking the second equation where f of I minus 1 is taken instead of f of I plus 1, then the equation will become dou f by dou x plus f of dou x by dou x at I is equal to f of I minus f of I minus 1 by delta I minus 1. So both these I and I minus 1 are the I mean delta xi and delta xi minus 1 is the same. Uh, we will be truncating at the order of delta xi minus 1. So we got two equations for dou f by dou x. From that we can take an average out of these two equations, because two of these equations are giving the same value. To get an idealized approach, we can get we can take an average of this, and by which we will be getting, we, we are simply adding this 1 plus 2, then we will be getting this kind of equation dou f by dou x is equal to f of I plus 1 minus f of I minus 1 divided by f xi plus 1 minus xi minus 1. If you look at here it is 2 times, that is uh, del xi plus 1 minus xi, and also x minus xi minus 1. 2 delta x's are present, so that's why it is converted to 2 times delta x. Similarly, this uh, dou square second order term can be written as twice dou f here from the previous equation. Previous equation was for This equation was for dou f by dou x, where the function was x. If we replace to get answer for dou square f by dou x square f, we can replace this f of I plus 1 and I minus 1 by dou f by dou x. From which our answer will be something like this one: dou square f by dou x square is equal to f of I plus 1 plus f of I minus 1 minus 2 times f of I by delta x square. So in our case, the question is asking for dou square u by dou square, sorry, dou y square. So instead of this one, the answer will be delta y square. So there is no such term in the options saying uh, uh, that answer. So similarly, if you consider u instead of f, here you can say, here you can see the uh, incremental equation in j direction, because our question is asking for uh, vertical direction. So that's why in the direction, that is, we are taking this way and this way. So that is going upwards is the positive, that is u I comma j plus 1, that will be given by u of I minus j plus uh, dou u by uh, dou y at ij into delta y plus dou square u by, there is some issue happen, the y is missing from here. So dou u by dou y at ij into delta y plus dou square u by dou y square at ij into delta y square plus etc. And again, if you are moving towards the uh, bottom direction or downward direction, then equation will be u of I j minus 1, which can be written in terms of uij as uij minus dou u by dou y at ij into delta y plus dou square u by dou y square at ij into delta y square plus etc. And if you are adding these two equations, we will get as for dou square u by dou y square, which is u of I comma j plus 1 plus u of I comma j minus 1 minus 2 times u at ij divided by 2 times delta y square. So this is the answer, but uh, this particular equation is not present in our options, and also we will have to uh, keep we use I for x direction and j for y direction, and that should be in ordered pair also. So there is no options in this there is no option in the given choices matching this particular solution. That's why we chose none of the above. Okay, hope everybody understood that. Moving on to next question. Next question is on the physics of the internal flow. Uh, Question is, consider a steady developing laminar flow in a circular pipe. Which of the following statement is true for this flow? Options are option A, velocity profiles. Sorry, the statements are first statement, velocity profile change axially. Second option, velocity profile changes radially. Third statement, pressure varies linearly in the axial direction. Fourth statement, pressure remains constant. And the options are, first option, statement 1 and 2 is true. Second option, that is B, uh, statements 2 and 4 is true. Third option, statement 2 and 3 is true. Option D, only first statement is true. So try to recollect uh, the physics of flow through a internal flow through a tube and trying to answer the question. So let's see the answer. Our answer is option A. That is uh, option, I mean statements. Statement 1 and 2 is true. That is the velocity profile changes actually. And second statement is the velocity profile changes radially. Let's check why is that. So here if you see, this is a image. There's an image showing the flow physics or flow physics of flow inside a tube. So from here the flow is entering into the tube. So at the entry it will be, the velocity will be uh, all in same direction, same magnitude. But once it enters the tube, the boundary effects starts to uh, act on the flow velocity, and due to that the velocity near the walls will be zero, and it will slowly increase from the boundary to the center region. So if you see, this is the developing length, and this is a fully developed region. So in the developing length you can see it's somewhat the uh, some portion is still keeping the uh, actual velocity intact, but here's a steady uh, change in gradient in the towards the boundary locations. So from on this we can see that in the developing length the velocity is The velocity profile changes axially. Also, the velocity profile changes radially. That is, if you see here, this is the axial direction. X is the axial direction, and this is the axial direction. If you see, this is the velocity profile at the entrance, but reaching here, it becomes entirely parabolic. So, the velocity profile changes axially. So, that's a true statement. Also, if you see this changes, that is how uh, the radial direction means it is the from center towards the outer wall. So in this direction also, if you see here, the velocity reduction was only this much, but if you see, it is almost reached to the middle of the tube. So in the developing region, the flow will be the velocity will be varying in the radial direction also. So both the statement, first statement and second statement is true. That's why that if you see here, the velocity profile changes axially. That is true, and velocity profile changes radially. The third statement was the pressure varies linearly in the axial direction and pressure remains constant. So if you see, this is the pressure plot. We see this is not varying linearly in the developing region. This is the developing region. In developing region, the pressure is kind of uh, decreasing, but not in a linear fashion. But if you see in fully developed region, the pressure is reducing in a linear fashion. So third statement is wrong. And also the fourth statement is saying the pressure is constant. That is also wrong because it is reducing. So there is only two statements true for developing and steady flow. That is given by the option A. Moving on to next question. Consider one-dimensional flow governed by dou square u by dou y square, or sorry, d square u by dy square is equal to constant over a height h. The interval h is divided into 30 equal segments. The upper wall moves to the right at a speed of 1 meter per second, while the lower wall is stationary. The number of discrete equations are. So the question is asking, if we have a one-dimensional flow in y direction governed by dou square u by dou y square is equal to c, and the entire length of the domain is h, and it is divided into 30 segments. So what will be the number of discrete equation if the upper wall moves at a speed of 1 meter per second and lower wall is stationary? So again, this is a question on discretization. Try to answer the question. So let's see. So this is the imagine this as the vertical height h, and it's been segmented to 30 segments. So this is, if this is one segment, similarly there are up to 30 segments. So if you see, if there is 30 segments, you can see from here, for two segments there will be 1, 2 and 3 points. So there, because to enclose two segments we will be needing 3 points. So to enclose 30 segments we will be needing 31 points. And it is given that the upper boundary is moving with a speed of 1 meter per second. So we know the value of u here, and also it is given that the bottom is fixed. So here u is equal to 0. So we know the values of the bottommost cell and the uppermost cell. So here uh, in this direction, in this case, we only have to solve for uh, how many segments. That is, we have 31 points, and we knew the condition at uh, uppermost and lowermost. So 31 minus 2, then we will be there will be 29 points remaining, and all these points we will have to discretize and solve. So our answer is 29. That is option. I think first option. Yes, option A. 29 is our answer. Moving on to next question. The question is asking the correct equation governing the fully developed flow in x direction through a rectangular duct is. So the question is asking for for the equation governing the fully developed flow in x direction through a rectangular duct. This is the duct. X of like this. So this is the x direction, y, z. So what will be the equation? Options are: option A, dou square u by dou x square plus dou square v by dou y square is equal to 1 by mu times dou p by dou x. B is dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu times dou p by dou x. Option C, dou square u by dou x square plus dou square u by dou y square is equal to 1 by mu times dp by dx. Option D, dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu times uh, dp by dx. So which among the following is the equation for the fully developed flow in x direction through a rectangular duct? So let's see the answer. We will be able to solve the question. So this is the uh, general equation, uh, including all the times for the flow in x direction. So equation is going to be rho times dou u by dou t plus which is a unsteady time plus u times dou u by dou x plus v times dou u by dou y plus w times dou u by dou z is equal to minus dou p by dou x plus rho gx plus mu times dou, dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So if we are having the see the question is given for fully developed flow in x direction. So uh, assuming the flow to be steady, this particular term will vanish, and also the for a fully developed flow in x direction, there won't be v and w components. So these two components will be not there. So these two terms will vanish, and again from the continuity equation, this particular terms also will vanish. If you remember that the continuity equation from all these terms will be equal to 0, then this equation will automatically equal to 0. So this will also vanish. Then we are left with the right hand side only, where this dou p by dou x will remain, negative gradient of dou p by dou x will remain, plus this we can neglect this particular term, that which is the body force. Then again dou square u by dou x square, because dou square u by dou x square is dou x is 0, then this term will also be 0. Then we will be left with 1, 2 and 3 times. So if we are rearranging, we are taking it on the other side. The equation will be dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu times dp by dx. Our answer is B. This is our equation answer. Moving on to next question. Next question is also on discretization. Which discretization method is known for its strict conservation property, making it ideal for fluid flow problems? Options are: option A, finite difference method; option B, finite element method; option C, finite volume method; option D, all of the above. The question is asking which discretization method is known for the strict conservation property. Try to answer the question. Our answer is option A, sorry, option C, finite volume method. Finite volume method is uh, known for its strict conservation properties. Because FVM enforces conservation laws, because it is FVM is basic step in FEM is we will be discretizing equation after integrating the properties over the integrating the partial differential equation. So that's why we are it is known that finite volume method integrates this conservation properties, because it is the our governing equation is integrated over the domain, which gives which entrust a strict conservation law on the domain of the method. Moving to next question. What is the main advantage of forward and backward difference schemes compared to the central difference scheme? So options are: option A, higher accuracy for all derivative approximations; option B, simpler implementation on non-uniform grids; option C, better stability for certain types of equation; option D, ability to handle complex boundary conditions. So which among the following is the main advantage of forward and backward difference schemes compared to the central difference scheme? Try to answer the question. So our answer is option B, that is forward and backward schemes requires forward and backward scheme only requires information from one side, but whereas uh, in central difference scheme requires, that is central difference equation requires information from both the sides. uh, So, several different equation cannot be defined in boundaries and such areas. Also, it can create some errors because it will be missing the actual value at that point. At that particular point, it will be missing the value. It won't include the value at that particular point. It will only taken from the uh, uh, two other direction or from the neighbors only. So several different schemes uh, might not be that accurate also. Next question. What is the primary factor to consider when choosing a meshing strategy for a particular CFD problem? Options are option A, cost of meshing software, option B, user experience with the meshing tool, option C, balance between accuracy, computational cost, and meshing effort, option D, availability of predefined mesh templates. So the question is on meshing strategy of a CFD problem. So what will be the primary factor to keep in mind while choosing a meshing strategy for particular CFD problem? Options are option A, cost of the meshing software, option B, user experience with the meshing tool, option C, balance between accuracy, computational cost, and meshing effort, option D, availability of predefined mesh templates. Our answer is option C, balance between accuracy, computational cost, and meshing effort. All the other thing is trivial cases. So our answer is option C, accuracy between the ideal meshing strategy should create a balance between accuracy requirements with the uh, computational limitations and complexity of the geometry and physics involved. Moving on to next question. Which of the following factors primarily influences the accuracy of CFD simulation results? The question is asking which of the following factors influence the accuracy of CFD simulation results. Options are option A, geometry complexity, option B, mesh type, that is structured or unstructured, option C, mesh density, option D, software used for meshing. You can try to answer the question. Which of the following factors primarily influences the accuracy of a CFD simulation results? Options are option A, geometry complexity, option B, mesh type, that is whether it is structured or unstructured, option C, density, option D, software used for meshing. Our answer is option C, that is mesh density. So mesh density mean similarly, if we are taking one particular area or volume, how much cells are there? That is called mesh density. So this mesh density directly affects the discretization of the governing equation, and it can significantly impact the accuracy of the solution. Answer is option C, mesh density. Moving on to next question. When comparing a structured and unstructured mesh with the same number of elements for a simple geometry, which one is likely to have a better solution accuracy? The question is between structured versus unstructured mesh with same number of elements for a simple geometry. So which among the two will likely to have a better solution accuracy? Options are option A, structured mesh, option B, unstructured mesh, option C, both will have same accuracy, option D, depends on the specific flow problem. Try to answer the question. Our answer is option A. Both can give good accuracy. Structured mesh with the same number of element can't typically offer uh, better control over element quality and alignment, leading to a potential higher accuracy for simpler geometries. So, answer is for simpler geometries, always structured meshes are better than unstructured meshes. Next question: how are boundary conditions implemented in CFD methods? Question is, how are boundary conditions implemented in CFD methods? Options are option A, they are applied directly at grid points in FDM or at element nodes at the FEM. Option B, source terms are incorporated into discretized equations. Option C, both A and B are used depending on specific boundary conditions. Option D, it depends on specific solver algorithm used. So the question is, how boundary conditions are implemented in CFD methods? Try to answer the question. Option A, they are applied directly at grid points or element nodes. Option B, they are included as questions all these or they are incorporated as will be source handy for the you discretized equations. For the option C, both A and B are used uh, depending on the boundary condition. When you are facing the, it depends on the specific solver algorithm used. This particular session will help you in recollecting all these. So all all this session will help. These are about these the topics discussed here are the important topics. So it will help you in the long term. I mean, in the exams. So please try to revise all this before you go for this exams. Thank you for joining. The answer is option C. Both A and B are used depending on specific boundary condition because giving boundary condition directly at the grid points is called Dirichlet method, and incorporating it as source terms within the discretized equation is called Newman method. So both options A and B are true, which is given at option C. Next question: which is the which of the following best define the Dirichlet boundary conditions for property phi at point B in a boundary? Options are dou cube phi by dou x cube. Option B dou square phi by dou x square. Option C dou phi by dou x. Option D dou phi b. So which of the following best define Dirichlet boundary condition for the property phi at point B in the boundary? So our answer is option D, phi b. So all these are in equation formats. So Dirichlet boundary condition we have discussed earlier in the earlier question. It is giving directly the values at boundary. So suppose this is our domain. Assume it to be a rectangle. So these are the boundary uh, places. Suppose phi is the property being evaluated inside the domain. So if we are giving phi is equal to some value at uh, suppose phi of a in this boundary and phi is equal to phi of b at this particular boundary. So phi b means phi at b or phi of b. Sorry, phi at b. So similarly, that assigning phi to a constant value. All other option is giving differential terms, while only option D is giving a constant or direct value for phi. Phi is equal to phi b. So our answer is option D. So that's all for today. Thank you everyone for joining. So keep in mind that all these